So let me start share my screen. Can everybody see this?
Yeah.
Okay. So today we're going to do some problems about Boolean algebra and relations and function. So here's the first one. So we want to prove the De Morgan's law in Boolean algebra. So we have to verify the below these two equations where the union of these two is the universal set and the intersection of these two is the empty set. So can anyone tell me first that why this is true? And why we wanted to verify these two equations to show that the De Morgan's law is true? Anyone? Okay, so let's think about this as so I'll just draw the universe set here. Oops. Here's the U. So actually the A dot B, we can write this part as A dot B. And this part is the A complement plus B complement. Ooh, so we want us to see that A dot B and union the A complement plus B complement is the universal set. And then there's no the intersection is empty set, which basically means that the complement of A dot B is A complement plus B complement. Okay, and so now we're going to use the Boolean algebra property to show these two are true. So let's start with the first one. All right, so how are we going to prove this? So what is the first step we want to do? Anyone, any ideas? We can use any of the properties except De Morgan laws in theorem 6. So what's going to be our first step? So we can start with using commutative by just switch this two. Oops. And then we can use distributive, just view this A complement plus B complement as a whole. So we have A complement plus B complement and plus A. And we need to time that with the A complement. So this part is commutative. This is distributive. Okay. So what should we do next?
Could you do associative where you like move the parentheses?
Yeah, we can do that, but just be like precise. We can use commutative again.
Oh yeah, yeah. So use commutative to like have a yeah.
And the second part, keep the same. And then we can use the associative. Oops. Okay, and what about the next step?
Negation.
Yeah, that is correct. Then we can use negation, but if you want to be precise, you can also use commutative again, just to switch the A complement plus A. But yeah, we can use negation. If we're using negation, it will become one, and this part was A plus 1. And what about next? Do you have a,
Universal bound.
yes, exactly. And what will this going to become to?
So it's going to be 1 time with the 1.
Yes, and that's universe bound. So right here, her 1 times 1, which is 1. So this is by identity. Okay, and now we have shown like the first part is true, and then we need to prove the second part, which the intersection of these two is empty. So, so A dot B. Okay, so we want to prove this. And we start with and what is the first step we're going to do in this one? It's just similar to the first part, but
Is there any way you can negate A complement plus B complement?
negate a complement plus B complement?
Like, is there a rule that parentheses A complement plus parentheses B complement can turn into A times B?
No, because you can only use the property list in the theorem 6. What you mean is that just negate the A, this? Is that what you mean?
Yeah.
If you just do negation of this, you won't get A dot B, like A intersection B. So in the De Morgan's laws, we have the A dot B complement is equal to. Wait, I think,
That's right.
yeah, I think you are right. So yes, we can negate the A complement plus B complement. But in this problem, we just want to use the property in theorem 6. So like using the commutative, associative, or distributive. So this, yeah, this should be equal to. A dot B. All right, so like anyone have any idea like how we want to start from this part? Because we want to use the property in the theorem 6 to prove this one.
So I think we can just do like you say, we do the De Morgan laws and then we use the negation to get the A times B times with like A times B negative. So it's gonna be equal to 0.
Yeah, so in this one, we wanted to we want to prove the De Morgan's law. So we cannot use the De Morgan's law. So actually
Oh, okay.
this part you're negating this one is actually using the De Morgan's law. Because we're trying to prove the De Morgan's law is true.
Can we do?
Can we do distributive?
Yes. So let me delete that first. Oh, oops. Okay. So we use distributive, and we can view the A dot B as a whole. So we have A dot B. And this is by distributive. All right, and what is the next step?
Commutative.
Yes, we wanted to switch the order inside of the parentheses to make it exactly the same as what we have in the theorem. And then similar, we can use the
Associate that, and then we have like B times A times.
yes, that is correct. Okay, and then what is going to be the next one? B dot,
Negation.
yes, negation, and which you enable is at 0 and plus A dot 0. And this is by negation. And then we're going to use which one?
Universal bound.
Yes, this will give us 0 plus 0, which is 0. And this is the last one is identity. Okay, and we're done with this problem. Any questions? All right. So the next one is relation arrow diagram. So we want to draw the two-side arrow diagram for the relation R, which R is defined as the n is the sum of the elements in S. So remember how we draw the two-side arrow diagram? So we first have the domain here, have a codomain. So the domain, we have the power set of 1, 2, 4, 8. And what's gonna be, sorry, that's 48. So we wanna write out all the subsets in the power set. So what are they? So we always have empty set. And 1, 2, 4, and 8. And what else?
2, 4, 2, 8, 4, 8.
Yes.
1, 2, 1, 4, and 1, 8.
2, 4, 2, 8. 1, 4, 1, 8. And we still have 4, 8. Okay, that's really bad. Okay.
I think we're missing 1, 2.
Yeah, we are.
Yeah, you're right. 1, 2. And we, what else?
3 and 4 also. Like 1, 2, 4, 1, 2, 8, 1, 2, 4, 8.
Yes, that's right.
And 2, 4, 8.
2, 4, 8. And the last one is 1, 2, 4, 8. It should be right. Make sure I didn't miss anything. Okay. That's really long. And what about the codomain? So the codomain, we have the set. So it's not the power set, but only the set itself, all the way up to 14 and 15. So what's going to be in the codomain? It will just be each element, right? 0, 1, 2, 3, 4, 5, and all the way up to 15. Okay. So how are we gonna match the domain to the codomain? Because remember, our rule is n is the sum of the elements in S. So here's your elements in S. All the sets we have here, and here's the n. So what's gonna so which element is empty set gonna maps to?
0.
Yes, because there's 0 elements in the empty set. And what about 1?
Goes to 1.
Yes, and 2 should goes to 2. We have 4 goes to 4. And what about 8? 8 goes to 8. Okay. Okay. And what about 2, 4?
Would it go to
6?
Yes. You see, just add up together to get 6. And 2, 8.
It would go to 10.
Mm-hmm. And 1, 4, we go to 5. 1, 8 goes to 9. And we have 4, 8 should goes to 12. 1, 2 goes to 3. Sorry, that's like Looks really bad. And what about 1, 2, 4?
7.
1, 2, 8.
11.
And 1, 4, 8. It goes to 13. And then we have 2, 4, 8. 14, and the last one goes to 15. Okay, and now we're done with this one. So just remember we would do it. Please just write that like vertical. Any question about this one? Okay, let's move on. All right, so we have now I have the composition problem. So we have the C, the power set XYZ goes to the power set XYZ, be the function with the rule CA, where the rule is your XYZ minus the A. And we have the set A, we have the relation A where your n is the power set XYZ goes to 0, 1, 2, 3. And here's the function of n is the number of elements in A. So which composition is defined? Say n or nc? Like, okay, so whenever you see like this, you probably see that in the math problem, where that basically means this. So you have like a function of cy, and you have a function of nx. This basically means your codomain of your function n is the domain of the function c. So you have the domain n, and then we have the codomain n, and this basically means the domain of C, and goes to the codomain of C. All right, so which one should be defined? Which one should go first? Cn or nc? Anyone, any idea?
CN. CN.
Okay. So if we have, okay, so let's write out the, domain and the codomain of each of them. So we have the power set. Okay, so if we're gonna do like Cn, which means we're gonna compute the number of elements in A first. And then basically which one is defined, we need to see if the domain, if the codomain of N matches the domain of C. So if these two can match together. So what is the domain of N? So domain of N should be like a bunch of numbers, like 0, 1, or 2, or 3, because that's like the number of elements in A, right? And the domain of C should be a power set. like the power set. So that basically means they are not matching. So in other words, the composition NC should be defined, but not CN. Does that make sense?
Can you repeat that one more time?
Yes. So, okay. So imagine we're doing the CN. And this basically means we're first gonna compute the number of elements in A first. And the number of elements in A was just a bunch of numbers, either 0, 1, or 2, or 3. So we get that as C is, let's say if it's 2. But right here, we know the rule for C, it has to be from power set to power set, but not a single element. That's why it's not defined, it's undefined. And if we check NC, so we first have, oh, what's wrong with that? Okay. And the codomain of C is also a power set. So we have like power set of 2. And that matches with the domain of N. So the only thing you want to make sure is that your codomain, your codomain, it matches the domain of the second one. So this one is defined. Because your codomain of C matches the domain of N. Here's your codomain of C, matches your domain of N. Does that make sense?
It makes more sense to me.
Okay, so now we see the composition of A dot C is defined. So let's start with the power set. So let's start with C first. So the domain of C is a bunch of power set. It's the power set of X, Y, Z. And it also goes to a power set of X, Y, Z. So what are the subsets in the power set? As always, we'll have empty set. And what else?
X,
Mm-hmm.
and then Y, and then Z.
Yes. Y, Z, and X, Y, Z. Okay. And it should be the same for this side. All right, so remember the rule for C is the power set X, Y, Z minus A. So imagine like all the left-hand side, this part is our A. And what is gonna the empty set match to? If you have a XYZ minus the empty set.
The set XYZ.
That's right. And what about X?
It's YZ.
And Y?
XZ.
Yes, and we have Z as XY. XY, you have goes to Z, and XZ, Y, and YZ, X. And then last XYZ, it will goes to empty set. Okay, and now we're finished the part that the computation going through from the domain of C to the codomain of C. And then we have the codomain of N, which is 0, 1, 2, and 3. So how is this part gonna match up? So right here we have this part is actually the domain of N. So how would you match the empty set to the right-hand side? So our N is the number of elements in the set.
It's 0.
Yes. So the empty set has 0 element, and X usually goes to 1 because there's only 1 element in the set X. Similar for Y and similar for Z. And XY should be 2, XZ, and YZ. And the last XYZ should have 3 elements in the set. And now we're done with the composition. So we start from the, let's see, we start from the X. And then we wanted to do the XYZ minus X. And that was pointing us to the YZ. And then you can count how many numbers are in the YZ set, which is 2. That's how the composition NC works. Any question about this problem? Okay. So the next one is a similar one. Consider the relation R on the set A 0, 1, 2, 3, 4, 5, 6 with the rule that XRY is X minus Y is divisible by 3, and draw the one set arrow diagram for R and R composition R. And describe the latter relation with an English sentence. Okay, so let's start with all the elements. So this is this one set arrow diagram. We don't need to write that like vertically. 6. So XR at Y basically means if X minus Y is divisible by 3. So remember 0 is also divisible by 3. And also negative numbers as well. So what number is 0 gonna point into? So imagine like you have 0 as x, and what number is it goes to have x minus y is divisible by 3?
So itself 3 and 6.
Yes, that is correct. So it can go to 6, and as well, 6 can also goes to 0. And y minus 1 is also 0. 2 minus 2 is also 0. So it all can goes to itself. And is there any other numbers that 1 can goes to?
See, someone in the chat also said 0 goes to 3 and 1 goes to 4.
Okay, 0 goes to 3. 1 goes to 4. And we have the 2, 5 left. Okay, and that is your one set arrow diagram for R.
3C2.
Yeah, sorry. 3 to 6, you're right. Make sure I have everything. Okay. This is R. And what about the R composition R? The one set arrow diagram R composition R. What is gonna look like? So R composition R basically means the codomain and domain are all the same. So if you enter in 0, and then you can go to, let's say you can go to 3. And then from 3, you can go back to 3 or go back to 0. So that basically means your 0, 0 is in the set of R compose R. And also 0, 3 is also in the set of R compose R. So if you list everything and you have found in the end, the one set arrow diagram R composition R will be the same as R. Does that make sense to everyone? Because you can always start from a number and then goes to the intermediate number and go back to itself. Like you have 1, 4. So 1, 4 is also in R compose R, because you can go from 1 to 4 and 4 back to 4.
Can you talk one more time about why is 4 go to 4?
Okay, so because we know in the relation R, we have 1 goes to 4, right? And that basically means we have 4 here. And then we start from 4. We do another computation. We also can goes to 4 from 4 in R.
Right.
That's why we have 1, 4 in R composition R. And then you can test like other numbers as well, like 6. You want to check if 6 is in the set. So you can have 6 goes to 3, and 3 go back to 6. So that will give you our composition of R will be the same as the one-side error diagram of R. So how would you describe the R composition R with an English sentence? So R means that x minus y is divisible by 3. But what about our composition R?
So does that mean the y subtract x is divisible by 3 too? Like the backward is also true for that case?
Yes, but the key part, the composition, is the intermediate step you're taking right here.
Okay.
So the first one, we start with x minus y is divisible by 3. And for our composition R, which introduced us an intermediate step where there exists number z such that, oops, oh man. What? Oh my gosh. Okay. Okay, so there exists z such that your x minus z is divisible by 3. And z minus y is divisible by 3. Okay, so we're done with this one. Any question before we move on? Okay, next one.
Sorry, in the chat, there's a question. Can you repeat the final sentence of the last problem?
Yeah. So there exists z such that x minus z is divisible by 3. That part is to represent this part. The first R. Your 6 goes to 3. And z minus y is divisible by 3, which is the second part. Okay. All right. Explaining composition. So this one should be quick. So let A is the set of all students in your school, and B is a set of all sections of all classes. And C is the set of all instructors. If XY belongs to R, means that student X is enrolled in course Y. and AB belongs belongs S means the course A is being taught this semester by instructor B. So what is the meaning of the relation S composition R? So we have R with student X. Student X is enrolled in course Y. And we have S is the course A is being taught this semester by instructor B. And what does S composition R means? Anyone? You would just need to combine the S and Y basically. So if we have X and Y in the composition of S and R, that means we have student X and instructor Y. Or I'm not sure if that way would looks better, XB. So the composition of S and R would just means that student X is in instructor Y's class. Or B. Okay, is that clear to everyone? All right, so next one is one-to-one and onto. So prove, okay, so we have like 1 minute left. Let's do this real quick. So we want to prove F is one-to-one and onto. So how are we going to prove if a function is one-to-one? Right? And you want to let fx1 is equal to fx2. And then you want to show that your x1 is equal to x2. That means your function is one-to-one. So if we plug in that, we have x1 cubed minus 2 and x2 cubed minus 2. And then we plus 2 on the both sides. We have x1 cubed equals x2 cubed. And this means x1 is equal to x2. Just a reminder, x1 squared doesn't mean, sorry, x1 squared equals to x2 squared doesn't mean x1 equals to x2. Because you might have negative numbers. So we're done with the one-to-one proof. You have shown that if fx1 is equal to fx2, then x1 is equal to x2. And how would you prove onto? What's like the general rule for proving a function is onto? So basically you want to show that let y be given and so we have x so set x is equal to the cube root of y plus 2, a real number, and then we can from the x y to plug in the y. Which will show that it is onto some number in the codomain. All right, and sorry, we passed like 2 minutes over. You're free to leave if you want. If you have any question, you can leave and ask. You can. Okay.
So sorry, I have one quick question. Like for the second part, when you saying about like how to prove that's onto, so does it mean that we have to prove every element on the codomain is we can find the one on the domain, right? Is that onto function mean?
The onto actually means that every element in the codomain can match to an element in the domain.
Yes. So in here you find you let the y is belong to R, so that means the y you pick here in the codomain, right?
Yes.
And yes, okay, thank you.
So you have the fx here and the y. So you have some numbers here, a bunch of numbers here. You just want to 4, 5, 6 to match numbers in the domain. That's
Yeah.
what onto means.
Yes, yes.
Or the other way. Sorry, should be the other way.
I had a question about the one of the problems we were talking about the relation of R onto R. Like where we were like
This one?
yes.
Okay.
I just got a little bit lost on this one. Could you just at least explain like where the arrows come from? Because I got really lost on that. I'm sorry.
Okay. So right here we have the. So this one, the arrow pointing to yourself, 0 to 0, which basically means this is your x and this is your y. So that basically means 0 minus 0 is 0, which is divisible by 3. That's how you can have the relations. That's how you can have the pair of 0, 0. And for the arrow pointing to like say 0 to 3, that basically means your x is 0 and your y is 3. Okay, and you say x minus y is divisible by 3. So you can have the relation of 0, 3 in your R in the set.
Oh, okay. I think that makes more sense. I just was lost on like where it comes, but I think now it just all makes sense. Thank you so much. Really appreciate it.
All right, I'm gonna stop streaming.
Cool.